And welcome back to the Amateur Radio Online Technician Licensing class, session 2B. I can't help it. I'm going to say 2B or not to be. I can't help myself. Okay, so this is a continuation from the previous video. Again, if you were taking the actual course, this would be part of the same session that we did on a Tuesday night. So we're going to now go into some things like Ohm's law and power laws, some other things that we're going to cover related to the components, the resistors that we just talked about, and then we're going to other components. So remember we were talking before about resistors and that they resist the flow of current and that there are different types of resistors, and you can calculate resistors with either in series, which summing all the resistors in that series pathway. We can calculate the total resistance of parallel resistances using the formula we showed you. And then if we have a complex network that is with series and parallel resistances, we're going to do the parallel resistances first, replace them with a equivalent 1 resistor, so we end up with a set of series resistances that we can then add up and to have the total resistance. So that's basically what we've covered with resistors up to this point. Now we're going to talk about Ohm's law, which is E equals I times R, remembering that E is voltage and I is current and R is resistance in ohms. So George Ohm figured it out that at a constant temperature, the electrical current flowing through a fixed linear resistance is directly proportional to the voltage applied across it and inversely proportional to the resistance. And we call this relationship between voltage, current, and resistance after him, Ohm's law. And you can see I've put the equation into the circle method. We have E, since it's left of the equal sign at the top, and I and R in the lower sections below. And that represents E equals I times R, where E is voltage. Now in some equations you'll see this is V instead of E. Again, I'm old school, so I tend to use E, but this is just as much today people using V instead. So let's calculate now. We want to find out what E is. That's our question here. And we have a current of 250 milliamps. That would be equal to 0.250 amps. So 0.250 amps is 250 milliamps, or 250 times 10 to the minus third, as you can see below. And then we have 4.5 kilo ohms, which is 4.5 times 1,000, or 4,500 ohms. And what we're trying to find out is what's the voltage in this circuit. So we cover the unknown, and the unknown here is E, so we cover E and we get the equation I times R. So we're going to multiply the current times the resistance, and we get 250 milliamps times 4.5 kilo ohms, which is now equal to 0.250 amps times 4,500 ohms, and we end up with 1,125 volts. We could also write that as 1.1 kilovolts as well. So 1.125 volts, or we can do a little rounding and make it 1.1 kilovolts. And how we found that was we covered the unknown in the circle equation, and we end up with the horizontal variables, which means we multiplied. So let's do this one. This is basically the same problem, but we're going to change to 10 milliamps, and remembering that a milliamp is 1/1000th of a amp, or 0.010 amps. Okay, again, same as before, we don't know E, so we're going to cover the E. We get I times R from the horizontal variables. And now we can see 10 milliamps times 4.5 kilo ohms, or 0.01 amps times 4,500 ohms, which gives us a value of 45 volts. So let's look at this problem. Now we have the voltage, we have the ohms, but we don't know what the current is. So we cover the I, and we get, because now we see it's vertical, because we cover the I, we see it's vertical. E is now over R, so we have E divided by R equals I. So we can now evaluate that. 13.8 volts divided by 4.5 megohms, and 4.5 megohms is 4,500,000 ohms. And we get an answer of 3.1 times 10 to the minus 6 amps, and 10 to the minus 6, excuse me, is micro, so we can replace the 10 to the minus 6 with the mu symbol and say 3.1 microamps. Now often we don't have the mu symbol available, So some people might use mm, meaning milli. So 3.1 MMA is 3.1 microamps. Now let's look at a practical example for a second. We have an LED diode. It needs at least 1 volt DC to turn on, and in this example it will be damaged if it draws more than 50 milliamps. It has an internal resistance of 1 ohm. Like I said before, everything except superconductors have some sort of inherent resistance. In this case, we're just arbitrarily saying that this LED, light emitting diode, has 1 ohm of internal resistance. Remember, 50 milliamps is actually 0.050 amps. Okay, so what current will result if we directly hook up this to a 3 volt DC source? Okay, so we don't know I, so we cover the I, and what do we get? E is over R, so E divided by R. So the equation is I equals E over R, or E divided by R, and we can see that 3 volts DC over 1 ohm is 3 amps. 3 amps is very much bigger than 50 milliamps, and unfortunately the diode has burned out. So if we want to protect this diode, we want to make sure we limit the current to less than 50 milliamps. Remember, one of the things we said a function of resistor is to limit current to protect components. So what resistance can be used to limit the current to 20 milliamps or 0.2 amps? Well, we don't know the resistance, so we cover R, and what we get is a vertical situation. E is over I, so we know we're going to divide. So R is equal to E divided by I. So R equal E divided by 0.02, or 3 volts divided by 0.02 amps equals 150 ohms. So if we place a 150 ohm resistor in the circuit in series with the diode, it will limit the current of that circuit to 20 milliamps, keeping it less than 50 amps and making a very happy LED to light up. And that's a practical problem in circuit design that we sometimes run into. So one of the relationships we have here besides Ohm's law is the power law. And the power law is P equals E times I. And you can see P is on the left side of the equals. So we put it at the top, and E and I are multiplied together, so therefore they're in the bottom section. So P equals, I often say P equals to I times Z because I remember it as pi, as an apple pie. So P equals I times Z. It's the same as P equals E times I. It doesn't matter. So power is the rate at which electrical energy is used. It's expressed in watts in our case. And 1 watt is the rate at which work is done. 1 ampere flowing through an electrical potential difference of 1 volt. So 1 ampere flowing through a 1 volt difference. And that would be 1 watt. And so the unit of P is watts, E is voltage, and I is current, again in amperes. So watt is a measure of energy. It can be heat from the radio. It could be the power putting out of the radio. It could be the heat from a light bulb. Watts is watts is watts. A 100-watt light bulb is like a 100-watt heating pad, like a 100-watt radio. Watts is a measure of energy. Doesn't say what kind of energy it is. It just tells you it's a measure of energy. And the circuit load may be expressed as a power being used. So I could have a 1500-watt hair dryer. I can have a 250-watt coffee maker. I can have a 20-watt low-power transceiver radio. So power is used to express the load. And the load could be anything that's powered by a circuit. Now remember, a load could be a DC circuit, could be powered by DC voltage, or it can be powered by AC voltage. Remember, when we power something by AC voltage, the voltage we use is the root mean squared. It's the VRMS voltage when we do the calculations, the DC equivalent voltage. And the transfer output, as I just said, is expressed in watts as well. And as I said when we talked about resistors in the previous recording, electrical components must be sized to handle the maximum number of watts they will experience. So if you're having a 50-watt device, you need something that will handle at least 50 watts. Oftentimes we go higher for safety, but it has to handle at least 50 watts. If it cannot dissipate that amount of energy, it's going to burn out. It's going to be damaged. So if the device is designed for 20 watts and you're running 50 watts through it, that device will fail. So you want to make sure anything that you're sizing must be handled the watts being experienced. Now these formulas, you can see there's a relationship between E equals I times R has a relationship with P equals I times E. When you look at the relationship, you can see they share some values. These because they're in the same family. And there's a relationship between these formulas. So let's look at what happens here with the shared values. The total resistance in example R of this circuit is 300 ohms, and the current I is a 1.45 amps. So what is the total power used? Now remember, we have a circle equation that says P equals I times E, but we don't know what P is. Okay, so we cover the P and we need I times E, but we don't know what E is. We need to find P, but we need to know what E is first in order to do the equation. So we do have another equation that relates these two together, and that's Ohm's law, and we have E equals I times R, so we cover the E and we find E is equal to I times R. So we have R and we have I, so we can now do the calculation. 1.45 amps times 300 ohms is 435 volts. Now we have E. We can go back to the power law circle. We cover the P and we get I times E. We know what E is now, so we get 1.45 amps times 435 volts, which gives us 631 watts. And what we basically did is a form of substitution. So we didn't do any algebra here. We just calculated with one circle to get the missing value from the other circle so we could plug it back in and solve the equation. So this substitution can be also denoted in this way. We took P equals I times E. We didn't know what E is, so what's E on the other equation? It's I times R. So what we essentially did was we said, okay, let's replace the E on the left with the I times R from the right. And P was equal to I times R, or it can be written in shorthand as P equals I squared times R. And that's exactly what we can do to solve the problem. I squared times R, we go 1.45 squared times 300 ohms. 1.45 amps squared is actually 1.45 times 1.45, and then the result we then multiply by 300 ohms, and we get 631 watts. So we could have done this with a substitution where we didn't plug in the numbers to the end, or as we did before, we actually plugged in and solved the equation separately, and then and brought one result to the other. Doesn't matter, each way works. Now, when you look at these equations further, there are about 12 different variations of these power and voltage equations, and you can memorize all 12 of them, and many people do. Sorry, I can just notice that the slide displayed with a P over R, square root of P over R, kind of incorrectly. I apologize for that. Sometimes when I'm putting symbols together, they show up differently than when they were not in slideshow mode, so I apologize for that, and I'll have to figure out how to fix that. But the bottom line here is that there are 12 formulas you can memorize, and that's up to you to memorize them. Or you can recognize that these two circle power law and Ohm's law, these two circles, actually were where these came from. And because that's where they came from, you could memorize the 12 or just use those two circles like we just did before and use substitution to calculate every one of these things individually without having to memorize the whole table. It's up to you. And of course, you will need a calculator to do the square roots. So again, some people do the memorization of all 12. Some people deduce it by using the circles every time they need it. It's up to you. So the other area that I'd like to talk to you briefly about batteries is about watt hours and amp hours. So a battery is capable of handling, in this case, 50 amps for 1 hour or 50 amp hours at 12.8 volts. So in theory, this will be able to hold 12.8 amps, 12.8 volts for the amount of time, 1 hour of 50 amps. So if I have a 50 amp load, it will stay at 12.8 volts for 1 hour. After that time, it'll be depleted and basically not be able to put out energy. And so power is equal, in this case, to 50 amp hours times 12.8 volts, and we get 640 watt hours. So the power here is 50 amp hours times 12.8 volts, which is 640 watt hours. And that's how much energy we could pull out of this battery. So if the average load from a transceiver is 8 amps, how many hours will this battery be sustained for? or how many, if the average load for the transceiver is 8 amps, how many hours, I'll have to correct this, will the battery sustain the transceiver for? So we have 50 amp hours divided by 8 amps, and we get this for 6.25 hours. Now, that 8 amps is an average reading. There are times when we're transmitting, we're going to pull out more power than when we're receiving, but that's an average. So we know it's probably not going to be more than 6.25 hours. If we're transmitting, it's probably going to be something a little less or about there, but it gives us a ballpark idea because it's an average that this battery will last 6.25 hours, and that's how much transceiver time we have in the field for it. Now, let's say I have a 2-cup 125 watt coffee maker and it takes 6 minutes to make coffee. Will this battery be able to power it? Okay, let's figure it out. We have 125 watts times 6 minutes equals 750 watts of energy used. Well, we only have 640 watts available to us, so therefore this coffee maker will not be able to boil the water in 6 minutes. It will deplete the battery long before then. So understanding these kind of calculations of amp hours and watt hours and what you're drawing tells you how long that battery will be able to power the devices it's intended to work for. And so if you're working in the field like I often do with transmitting out of parks or at campsites, then I carry enough batteries sufficient for me to operate for the period of time I'm away at the power levels I wish to be at. So if I'm on average, I don't use more than 20 watts when I'm transmitting. So therefore, I can have a battery load that will last me for 12 to 24 hours, depending on which radio I'm using, which battery I'm using. So I have a number of different batteries. And so I choose the one that's going to last me for the time that I'm out there, and then I recharge it. Or if I'm going to be out for a prolonged period of time, I have a battery that I use, and when it's starting to deplete, I bring in a new battery, and I take the other battery and I attach it to a solar charger. And while I'm working for the next 6 or 8 hours with that new battery, I am charging the older battery, and then I begin leapfrogging these as I go. So let's talk about some other circuit components, capacitors and inductors, and these are going to get funny, so to speak. These are kind of funny devices. And we're not going to go into a heavy amount of detail on these, but later on in the general and extra, you'll go into a little bit more detail on these. And this is where AC becomes a little bit more spooky compared to DC, but it also makes it kind of fun. We're not going to go heavy, but we're going to go deep enough to give you an appreciation of it. So in the wacky world of capacitors, capacitors are basically in their simplistic form are a plate separated by a dielectric or an insulator and another plate. So we have two conductors separated by an insulator, and that is a capacitor. And capacitors store charge, and the charge is stored as an electrostatic field on insulated conductive surfaces. So there's a charge on both plates, and the plates are separated by an insulator. Now, capacitors block the flow of DC, and when they're charged, they act like a battery. So if I put a battery to a capacitor, what's going to happen is it's going to start building up electrons on the plates. It's going to charge up, and as it charges up, it's going to reach only the level of the battery. So if it's a 5-volt battery and the capacitor is rated for 5 volts or more capacity, then that capacitor will charge to 5 volts, and then because it's fully charged, you cannot put any more energy into it. It's done. And so no more current will flow. So once it reaches the maximum number of volts based on the power coming in, it's going to stop the current flow because now the water level, so to speak, is at the same of the source as it is in the vessel. So now there won't be any flow. And what I can do is I can disconnect it from the circuit. I can go walk it over to another circuit, and I can plug it into another circuit that takes up to 5 volts. And it'll begin powering that circuit because it's going to discharge into that circuit because there's no resistance at that point to DC flow. That other circuit wants power, so it's going to discharge the electrons into that circuit, and it's going to run it for a period of time until it dissipates, just like a battery, until it's fully drained and it loses all of its charge, and then it will stop being able to power that circuit. So yes, what happens when you plug a DC or a capacitor into a DC source, it will start charging up very rapidly to the same level as the DC source, and then it will stop the flow of current because there's no more charge you can pump into it. So the current will stop, and I can literally take it somewhere else disconnect it and take it somewhere else, and for a short period of time, power something of that same voltage. But where capacitors really come into their own is they do allow the flow of AC. And I won't go into details of how they do this. You'll learn this more as in the general and extra class. But just to say that they allow the flow of AC. And they appear to AC as a resistance that varies with frequency. They appear to AC as a resistance that varies with frequency. And we measure them in capacitance, and the unit is a farad. And generally we're dealing with micro, nano, and picofarads. So very small. You might find 1 farad and more capacitors, which are fairly big, used in uninterruptible power supplies in computer networks. So oftentimes if you lose power in a computer network, there is a set of large capacitors that begin powering the computer network until the alternate power source can come on. Okay, and of course the key thing is they have to be sized for the voltage that you're using. So if you're a 3-volt capacitor and you have a 10-volt circuit, that's going to overpower that resistor, or that capacitor, excuse me. It's going to overpower that capacitor, and that capacitor will blow. It will blow. So you want to make sure your capacitor is sized for the voltage it will have to be dealing with, at least to the minimum of the voltage it has to deal with. Ideally, more than the voltage it has to be dealing with, because that's a safety factor to keep it from popping. And we have, excuse me, we have fixed capacitors. You can see on the right-hand side symbols for fixed capacitors. And you see a curved line and a straight line. That means it's polarized, which means there's a plus side of the capacitor and a minus side of the capacitor. Many capacitors are not polarized, and so they have 2 straight lines in their symbol. Electrolytic capacitors are polarized, and you can see them because they have a positive sign on them. An electrolytic is a special type of capacitor. Again, we're not going to go into that level of detail. And then we have variable capacitors that can change the capacitance based on rotating a shaft. Just like we did with the potentiometer and resistor, like the volume control, we can vary the capacitance by rotating plates across the space to change the capacitance of a circuit. And where do we use this? Oftentimes when you're tuning a radio, what you're really doing is changing these capacitors. These are variable capacitors that are being adjusted as you tune a radio, as an example. And then below we have pictures of different types of capacitors. None of them are variable. We see the picture of the variable one with above it with the rotor and the stator. And then these are fixed capacitance. So we have the blue one, which is a 470 microfarad capacitor rated for, it looks like, can barely see it, 16 volts. And then we have some very small capacitances on the right-hand side. So they come in different shapes and sizes because of different needs. And they're a little bit different than resistances. So if you remember, in a series resistance circuit, we just added up all the resistances to get the total. This is the reverse for capacitances. So in the capacitance, when we have series, we use the 1 over 1 over C1 formula, plus 1 over 1 over C2, etc. And in parallel, we just add them all up. So it's reverse of resistance calculations with capacitances. Now, again, we're not going to go into detail, but I just want to give you an appreciation for it. Remember I said that a capacitor's resistance changes with frequency. In AC, in alternating current, we use the term reactance instead of resistance. Resistance is a direct current value. Resistance is DC value. Reactance is an AC value. They're both measured in ohms. We use reactance because it changes with frequency. So the formula, which again you're not going to have to worry about, X of C, which is capacitor reactance, equals 1 over 2 pi, which is 6.28, that's a constant, times the frequency in hertz times the capacitance in farads. And as you can see, the reactance on the vertical axis is going from 0 to 350 ohms, and on the x-axis or horizontal axis it's going from 0 to 900 megahertz. And so we can see the blue line. We can see that as we go increase the frequency, given that we have a 2 picofarad capacitor, that's 2 times 10 to the minus 12 capacitor, 2 times 10 to the minus 12 2 times 10 to the minus 12 farads or 2 picofarads. We're going to hold that the same. That's not going to change. But as we change the frequency, you can see the reactance, or the amount of ohms, the resistance AC flow, is dropping. And you can see for a 100 microfarad capacitor, we can see the same calculations. In this case, the frequency starts at 0.5 hertz and goes to 100 million hertz, or 100 megahertz. And you can see the reactance in ohms is going down from a very large number, 3.2 gigaohms, down to 16 ohms. So AC resistance, again, is called reactance. And as you increase the frequency, capacitive reactance goes down. Now, when we get to 0 DC, the equation becomes undefined, so we can only approach something up getting towards 0, but we can never get to 0 when we have an equation like this. And again, you're not responsible for for the formula and calculating this as a technician, but just so you know, because this is a very important property that you'll find out soon. So again, reactance is resistance originating from capacitors and inductors. So let's talk about the magnetic world of inductors. Capacitors are electrostatic. Inductors are magnetic, or magnetic field devices. So as current flows through a wire, as we remember, it produces a magnetic field. And we have, in this case, a coil. It's got an air core, that is, there's nothing but air that flows through it. We have a copper wire that's made into a coil. And inductors store magnetic energy in electric fields. So remember, when we pass electric current through a wire, it produces a magnetic field. And so this coil is used to store that magnetic field. So DC has straight wire resistance in ohms, but resistance that resists the flow of AC current. So whenever we have an AC current, we're going to, in a coil, an inductor, which is what a coil is, we're going to have a change in resistance of AC based on frequency. Just like in a capacitor, the reactance or the resistance changes with frequency. Same as in a coil, the resistance varies with frequency. And you can have an air core, or it could be a material that helps concentrate the magnetic field, like iron. So you can have an iron core or different types of iron type derivative cores to help you concentrate the magnetic field in the coil. And the unit for inductance is called the henries, and it's millihenries, nanohenries, and picohenries. And a transformer, which we'll learn about in a little bit, are 2 or more coils that are built to transfer energy between them. So we're going to learn about more of them in a few minutes, but really two inductors, 2 coils of wire, inductors, that are in proximity to each other. One has energy going through it, the other will have an induced current going through it. And we'll learn more about that in a little bit. And so here we have some symbols, schematic symbols for inductors. You can see there's an air core, and then you can see with 2 lines we have an iron core. We have, with an arrow, an adjustable inductance, and that could be representing with an arrow across the coil, or like with a potentiometer, an arrow in the middle of the coil. And we can also have a wire that comes out of different various places on the coil, because they have different levels of inductance for each of those, called taps. And then you can see below many different types of coils or inductors, but you can see what they have in common, and they all are wound wire. So all inductors are wound wire coils. And what's nice about this is calculating inductance follows exactly the same as resistance. So when you have series inductors, you just add all the inductances together. When you have parallel inductances, you use the 1/1 formula, just like in the same format you did with resistors. So inductors and resistors follow the same formula pattern, and capacitors are exactly the opposite of the resistor-inductor formula pattern. Now, inductance, as we said, is inductive reactance, which is the resistance that an inductor has to frequency, will vary with frequency, and the equation is X of L equals 2 pi F of L. And as you can see, as the frequency increases, the number of ohms, the resistance to the AC current, is increasing. And you can see that with the table below. We have the graph is 2 microhenries versus frequency, and the table is 1 millihenry with respect to frequency. And you can see in the table and the graph, as the frequency increases, the resistance increases, which means it's the exact opposite of a capacitor. The exact opposite of a capacitor. So impedance is the total AC and DC resistance of a circuit. So we have reactance, which is the AC components of resistance from inductors and capacitors, and we have impedance, which takes it and brings it all together, which is inductive reactance plus capacitive reactance plus the DC resistance. And the symbol for impedance is Z, and the units are ohms. So if X of L and X of C are opposite signs, that is, remember, one is increasing with resistance and one is decreasing with resistance. So one is going down or negative with respect to one going up. So X of L and X of C are opposite signs in the same magnitude. They cancel themselves out. That is, X of L becomes plus minus X of C, and if they're the same value, 200 X of L plus minus 200 X of C equals 0. And what you have remaining is the R, or the DC resistance. So then Z is equal to R, when X of L cancels X of C. So we can see the graph here of the relationship between X of L, the inductive reactance, versus the capacitive reactance. And as I said, they're opposite. So as the frequency goes up, which is the x-axis, the horizontal, you can see the X of L goes up and the X of C goes down. And there is a place where, for a given circuit, the lines intersect. And where the lines intersect, that means the value of X of L is canceled by the negative value relative to the curve of X of C. So interesting stuff happens at that point. Interesting things happen at that point. So here we have on the far right a kind of a circuit that we're talking about. We have an antenna. There's a symbol for an antenna. It's going into what's called an LC circuit, which is an inductor and a capacitor. And remember, they have resistance with frequency. So if X of L is canceled out by X of Z, that is, there's 0, an AC circuit means the only thing that's left is the inherent resistance of the circuit, and that is called resonance. When we are at resonance, we have X of L being canceled by X of C, and the only thing remains is the inherent resistance of the circuit. So if you think about this, if we have all these resistances, X of L plus X of C plus R equals the entire impedance of the system, and we get to a situation where X of L minus X of C cancels each other out, the only thing that remains is R, which means that is the maximum current flow in this circuit. Because if it was anything other than the same frequency that cancels these out, there would be additional resistance from L and C. So if X of L is not equal to X of C in magnitude, then there will be values that we're going to add together to R, and it'll be higher than when they're canceled out. So when L and C cancel each other out in a circuit, it's at resonance. And resonance only occurs at one frequency. And so this antenna can be designed to operate so it maximizes the current from the antenna to the radio for one specific frequency. Now, if we alter, we can make these variable. We can make a variable inductor or a variable capacitor, one or the other. If we vary L or we value C, it doesn't matter which one we vary. What we can do is vary it so that we can change the resonant point of the circuit. When we change the resonant point of the circuit, a different frequency will have the maximum current flow. And this is how you tune a radio station. This is how you tune a radio station. When you get to the exact station you want, it means that the X of L and X of C have canceled each other out, and you have the maximum current flow to the radio for that station. If you start moving, if you didn't change those and you started moving, if you could move away and look at the other frequencies, you wouldn't hear them as strongly. And you'd have to retune the radio to rebalance it back to get X of L minus X of Z at 0. And again, you'll learn more about this later, but this is called resonance. So I said I'd get back to transformers, and we'll do that for just a second. So a transformer is two inductors, generally wound on an iron core or some sort of core, and one is a primary coil and one is a second. Now, even though they're on the same core, they're insulated wires, and even though they're on the same core, there's no physical attachment between the left and right sides. The primary coil actually may be wrapped next to the secondary coil, but they're insulated, so they actually have no electrical connection between the two of them. And you can see that in the schematic symbol on the right, where you see the primary circuit does not physically come in contact with the secondary circuit. And the way this operates is through mutual inductance, the ability of a magnetic field in one coil to create a field in the other coil. So if I put current through the primary coil, it's going to produce a magnetic field. When that magnetic field is being produced, it actually is in close enough proximity to the other coil that it induces a magnetic field in the other coil. And if you have a magnetic field in the other coil, you must have voltage and current, because that's the nature of the beast. And therefore, you now have current flowing in the secondary coil that's proportional to the current flowing in the primary coil. So as I said, the core can be metal or a ferrite component. Ferrite is an iron-based ceramic compound. It conducts electricity. And we can transform voltage levels, match impedances, and also provide circuit isolation. Because remember, these two coils don't touch each other. It's through mutual inductance. So if there was damage or something that happens in the primary circuit, it will not affect the secondary circuit. So it forms a way of isolating one circuit physically from another, even though there's a magnetic field that's touching in common between the two of them. So let's talk about different types of transformers. You can have a step-down transformer. So a step-down transformer basically takes a signal of a value of X and steps it down to some value of X minus Y. And that's a step-down transformer. Now, when you do the calculations for power, the power on the left side, the wattage on the left side, will still be the same wattage on the right side, although the voltages will be different, because then the currents will compensate. So when you step something down, the voltage goes down, but the current capacity goes up. And the other side, if you step something up, the voltage might go up, but the current capacity, carrying capacity goes down. So conservation of energy, the power, of course, will stay the same. 100 watts on the left side will still be 100 watts on the right side. But we can change the voltage in this case. We can step the voltage up from some value to a higher value. Or we have an impedance change where we can have an impedance that's, let's say, 25 ohms and we need 100 ohms. So we can now wrap the coil such that we can have a turns ratio that will allow us to step up the impedance to a higher value. We also have an isolation transformer where we don't change the voltage or the current or the impedance. We just isolate the circuits from each other. So step down, step up, and isolation transformers are the three types of transformers. And as I said, the power will always stay the same. So here are the symbols for the transformers. We have a isolation transformer is T1, a step down transformer is T2, and a step up transformer is T3. So we notice we use the primary is always on the left, and that defines it. So the primary and secondary on T1 are the same number of coils, so it's isolation. It's a unit, no change in the voltage or the current, it's just isolation. T2, we use the primary as the left side, so that's the reference, and we can see that the right side there's less coils, so it's a step down, and vice versa on step 3. If you actually wanted to calculate the turns ratio and the voltage, again, E here can be used for, it can become V, they're interchangeable, E or V is interchangeable. We have the ratio, the voltage of the secondary over the voltage of the primary has to equal the number of turns of the secondary over the number of turns of the primary. And you can use some simple math to calculate the missing one. If you need a 1 in your own coil, you can then figure out which number of windings you need based on this formula. So you're not necessarily have to do that kind of calculation in the technician class, so I'm going to skip over this because I use this slide for the general class as well. But just understand that we're really just working off that previous formula. So let's just, as we're heading to the tail end here, let's just do a few more components. Switches and relays. We talked about switches on 2A in session 2A. And an open switch is one that has infinite resistance. Okay? And a closed switch is a conductor. It's just a piece of wire, so to speak. So when we open a circuit or open a switch, we're basically turning the power off or the current flow off from that circuit. And when we're closing a switch, we are now turning on the power or allowing the current to flow through the switch. Now switches are basically called poles and throws. So the picture in the box, we have one item that's being switched. So you can see one dot on the right of the open switch. That is one dot and one dot on the left. So we're only switching one side, one thing. And so it's a single pole. and there's only one lever on the switch because it only has one item that it has to switch, so it's a single throw. What you see on the right side is we now have a switch that has two outputs it's switching on. So the switch has two levers. Now there may be one lever when you're outside the box of the switch, but inside there are two separate circuits that may be switching two separate things. And we call that a double pole because there's two dots on the right and it's being controlled by two switches, so it's a double throw. And so these are contact switches that once you close them, they stay closed, and until you open them. So you have to throw the switch to close it, and it stays closed until you open the switch, both on the right and left, the SPST and the DPDT. This is a symbol below for a momentary contact switch. It's spring activated, that is, it's spring resistant, which means when you push down on it, it will have a spring that pushes it back up. So you push this down, it activates the circuit it's attached to for just a moment, and it springs back up and opens up again. So that's a momentary contact switch. We also can have a switch that can be powered by a coil. So here we have a coil. Remember, when you run current through a coil, it produces a magnetic field, and if the throw part of the switch is a compound like iron or steel that reacts to a magnetic field, that is, it's attracted to a magnetic field, then it will pull down and go to the thing that we want to switch, just the circuit that we want to switch, and it shorts out and causes a current to flow. So we apply control voltage to the coil. It creates a magnetic field, which is an electromagnet. Because the throw on the switch is an iron compound, it will then push down and make contact with the circuit and then allow current to flow. When we turn the current off on the control coil, it will demagnetize the coil, and the switch will then pop back up and open up again. These are called relays. There are solid state relays, there are mechanical relays, there are reed relays, there are different types of relays. But what are they for? Well, one thing they can do is you can have a switch that can handle huge amounts of current, 10, 20, 30, hundreds of amps, that have big contacts that are very dangerous to handle. They can create some very high sparking when the contacts come in close contact with each other as it's closing. So we would have a voltage that allows us to control that switch so that we are not in an unsafe condition if we had to throw it manually. And we can actually have that switch controlled by a computer or controlled by another voltage source in a remote location, so that we can control something that takes a high current flow remotely, or control something that we need to have a process control and we use to have a computer control. We can use a relay to do that as well. Then we have some protective components, and you're probably familiar with a number of these. We have fuses, which you see a lot of times in automotive fuses, fuses in different devices. All fuses have the same thing. They basically have a wire running through them, and some type of wire. And the wire is designed to burn up. Basically, it's designed to melt and fall apart. So when the current rating of that fuse is 1 amp, it means that the minute that fuse senses that there's more than 1 amp in the circuit, that wire starts heating up very rapidly because it cannot handle the amount of power running through it, and then it basically burns apart and opens the circuit and protects it. A circuit breaker is basically sensing that temperature. It has two different metals that have two different expansions rates on them, and then as this begins to heat up because it's going beyond its current carrying capability, it heats up, and then it triggers, the expansion triggers a spring, and it opens up the circuit. And so that's what's happening there. Then we have some other protective components. We have a lightning surge protector, which goes on antennas. So if your antenna is struck by lightning, we don't want that lightning to go to your transceiver because it'll literally burn it up. So we have a special device called a lightning surge protector, so that when the voltage is very high, it senses lightning. It has a special device that fires off and shorts that out so that it goes to ground. So it bypasses your transceiver and goes to what's on the left, a ground rod. And the ground rod takes the energy from the lightning bolt and basically moves that energy to the ground and protects your radio. Inside of a Radio Shack, if you have multiple radios, we always tie them back to one ground plate, one central ground. Again, you'll learn later why we do that. But we only tie everything back to one ground plate in a shack when we have multiple radios to protect the radios from any damage. The average person who only has one radio doesn't really need to do this, but we do it when we have multiple radios in the shack and multiple devices. Semiconductors. We have three different materials that our semiconductors are made of: silicon, gallium, and there's also LEDs. And they have different voltage potentials that make them work. Silicon is 0.7 volts, gallium is 0.3 volts, and LEDs are 1 volt, all DC. So semiconductors are made from silicon or gallium with the selected impurities built into the crystal lattice. That's called doping. You can dope the material so it could be a P material, positive material, or you can dope it for an N-type material, negative material. Combination of these materials form diodes, bipolar transistors, or field effect transistors, and many other types of devices. And you can see a listing of them on the right in their schematic symbols. LEDs, voltage variable capacitors, thyristors, triacs, Zener diodes, tunnel diodes, bipolar transistors like PNP transistors, NPN bipolar transistors, and then field effect transistors called P-channel, N-channel, junction field effect transistors. So many different types. We're not going to go into detail here in this course on those. But diodes conduct only in one direction and go from P to N material, and they block the flow in the reverse direction. Bipolar transistors either are PNP, as I said, or NPN, and they have three elements to them: a collector, emitter, and a base. And field effect transistors contain N or P channel. In an opposite substrate, there's a gate, source, and drain. So in a bipolar transistor, we usually put the signal coming in on the base. The small signal coming into the base, and that controls the current flowing between the collector, and the emitter. So let's go a little bit more about diodes. They conduct only in one direction, I said. So here's the symbol for a diode, and we have an anode side, or a plus side, and a cathode side, and a negative side. So the plus side is the P material, and the negative side is the N material. And so we have, between these two materials, they need a certain amount of energy to make this conduct. And so we call that the barrier potential. For silicon, as we mentioned before, it's 0.7 volts. For gallium, it's 0.3 volts. And for LEDs, it's 1 volt. And so, as I just said, listed here on the screen, and whoops, and just to finish up that, diodes, because they conduct only one direction, as we talked about earlier in session 2A, if we put an AC current on the left side, the P side of that diode, it's not going to conduct the negative side. So therefore, we're going to get pulsating DC out of the other side. It's only going to turn on when it's positive. It's going to ignore the negative side of the sine wave. So let's talk really quickly about some amplifier theory, because a lot of times people have a misconception that amplifiers basically create energy, and they actually don't create energy. A 100-watt amplifier is not creating 100 watts. It's using 100 watts that's been supplied to it. It's what is happening to the input signal that we're going to talk about. So amplifiers use a small signal to control a larger current or voltage source. So if we have a small signal, like from a radio antenna coming in, it's a very small signal, and we need to amplify that, what we're going to do is we're going to take that small signal and use it to control a larger flow or larger energy source. So the valve controls, in this case, in this illustration of valve, we have the water source again, we've used those before, and we have a pipe that has a value when it's fully open of 800 units. It can flow a max of 800 force units. And the valve, it should be a valve, I'm sorry, I'll have to correct that. The valve controls the rate of flow, and the valve spans from 0 fully closed to 5 fully open. So any value in between those are illegal values. And so in this case, we're showing it fully open, and it can let a flow of 800 force units through it. Now, that's where we're starting for, so let's put that down as we have a small signal, 5 volts, that's the input signal. And now we see that that 5 volt signal is got a value on the output side of 800 force units. Now we've quarter closed the valve. We've closed the valve by 1/4, and now we have something less than 800. We've reduced the flow through the pipe, so we only have 600 force units. We've made it half closed. Now we only have 400 force units. So now we have, for half closed, we have a 2.5 volt signal is now causing a 400 unit flow. So you see the amplification? The small signal went from 5 to 800. It went from 2.5 to 400. And so there's where the amplification is coming from. It's not that we created energy. The energy is what we had in the circuit already. We're just using a small signal from the, let's say, the antenna to control that larger flow. And so now we make it fully closed. We've reduced the flow to 0. And so now we can return the valve to half closed. And you'll see the value goes from 2.5 volts and has a value out of 400 off the larger pipe. And if we bring that to fully closed again, fully open again, sorry, then we'll go back to 5 volts, which means we'll have a flow of 800. And so the signal, the small signal, is being mirrored in the larger flow, and that's amplification. In a transistor, in a bipolar transistor, we have 3 components, a base, collector, and emitter. And the collector is where the majority of the source for the voltage and current are coming from. And we're using this little gate area to hold back that current flow. Now again, this is illustration. This is not the real way it works, but this gives you an illustration. It's an analogy. And so you look at the B line, you'll see a small gate that's controlling the bigger gate. And so if you have a small flow starting to go in, flowing down that B line, and it pushes enough force on the B line, it can open up the C gate. And so that's what we have in the lower picture. The small force on the B line has opened up the C gate, causing a larger current to flow. So that's basically how a transistor works as an analogy. And that ends the discussion we're going to have for tonight on components. And we'll take it from here for session 3. We'll start getting into more about propagation and antennas and feed lines and for next time. And again, if you have any questions, please email me. I'll be happy to take your questions by email at w7dao@arrl.net. arrl.net, sorry, getting a little tired. So thank you very much for listening, and hope you tune in for the next session in about a week. Thank you very much. Good night.